Hello, everybody. I like all you guys' pictures. Look good. Julia, I like your picture of your dog. That's a great picture. All right, let's see here. Let's see. There was something I was going to say. Yeah, there really was. One second, let me get the chat going. Yeah, okay, chat. You stay over here. Sorry, there's like a million things on my screen here. Okay. Why are you not working? Sorry, I'm trying to do stuff and it doesn't seem to want to work. There we go. Oh, 3 times. Great. Okay, there's a link. There's the link 3 times to the attendance form. Please go fill out the attendance form as usual. Grab this here. There we go. So I know Merckx's class has a. Oh, I know what I want to do. I want to make sure my microphone was right. Sorry, just one sec. Okay, yeah, we're good. All right. So I know Merckx's class has a midterm tomorrow. Is that still true? You guys have a midterm tomorrow? Sorry, my chat disappeared. Where'd you go, chat? Yes, okay, cool. Thanks. Yeah, I figured as much. So I figured we should mostly talk about stuff for the midterm tomorrow. Also, I'm planning on sometime later today, hopefully early this afternoon. Oh, excuse me, sorry. Early this afternoon, posting up some sort of practice midterm with solutions. So if you need more practice materials, that'll be there for you. I will either post an announcement. Do you guys see the announcements when I post them? Like, do you get notified in some way right away when I post an announcement? Okay, great. Then I'll make an announcement letting you know that there is a practice exam of some sort and solutions. It'll be in the modules tab, and that'll be there for you. Hopefully early this afternoon. I think I already have one ready to go. I just want to look at it and make sure that it is has appropriate questions, or if it doesn't, I can tell you not to do those. So I'm sure you guys have questions you want to ask. I've got Merckx's kind of review sheet up so we can look at that. But before we get there, there were a couple questions people asked me via email that I just wanted to make sure I addressed. So let me get to those first. And then after that, if you have questions, you can either type them in the chat, or you can ask them via your voice or whatever. Or you can reference questions that are on his practice list. So there was one question about a cost function. So I have this actually already set up to go. Also, let me just, there's the attendance form again. Please go fill it out once and only once. So this question says that the cost, so I forget exactly what the words were, but it starts off with dc dx. That's the rate of change of the cost with respect to x is equal to 1/50 of x plus 30. There's also a fixed cost when x, the number of units is 0, or the number of things you're producing is 0. The fixed cost c is 1,000. Another way of thinking about this is that c of 0 equals 1,000. They want you to find the function c of x. So this is very much what's called an initial condition problem or initial value problem. There's also a discussion thread about a different problem, I think, from the quiz that's similar to this idea, where you have to find the antiderivative, and then after you find the antiderivative, you have to plug in your known values so you can solve for the constant c. It's kind of unfortunate they used capital C as the function name here, because we also use capital C for the constant, but well. So if I was going to anti-differentiate this, so the antiderivative of 1/50 of x, well, that's just going to be 1/50, right? The constant multiple hangs out, and then the antiderivative of x to the first is x to the second divided by 2. And then the antiderivative of 30 is just 30 times x. And remind you guys, whenever you antidifferentiate a constant, you just get that constant times x. And then lastly, we get plus c, the constant. You might call it something different here, just to like make sure you don't get confused. So if you can always use a different constant name. Let's call it k. K is another typical name for a constant when we're doing this. All right, I might simplify this. So I've got c of x equals x squared over 100 plus 30x plus k. And then I'm going to plug in 0 for x and 1,000 for c to figure out what the constant k is. So plugging in 1,000 for c and 0 for x, these terms are just going to be 0. So we end up getting, right, those go away. So you end up getting just k equal to 1,000. Now, we found all the things we needed to find, but we haven't actually written the answer yet. So the question they're asking for is to find the function c of x. We have to write c of x, but we have to plug back in the actual value for the constant k. So our final answer should actually be c of x is equal to this function, x squared over 100 plus 30x plus this value here plugged in for k. And that would be c as a function of x, or the cost as a function of x. Are there questions about that? Sorry, that's the fall in the way. Okay, let's move on. So there were also questions about the quiz that Merckx gave the other day. And I know the person that sent me this said one of the things they didn't have a question about. Let's just go ahead and look at the whole thing. So I'm looking at the quiz number 2, and we will go through that real quick. And actually, I'm going to start with question 3. Oh, go ahead.
I have a quick question about like the c constant. Is there any time when you don't include that?
So yes, if you're doing a definite integral where you're finding the area, for example, so just to switch gears, right? If I was doing a real easy definite integral, like the integral from, I don't know, let's say 0 to 3 of 4x cubed plus e to the x. Let's say I was doing that definite integral where I was trying to find the area under the curve. Then when I anti-differentiate this, the antiderivative of 4x cubed is x to the 4th, or 4x to the 4th divided by 4, but then the 4's cancel. And the antiderivative of e to the x is e to the x. And then I could write the plus c, but I don't need to, because I'm going to end up evaluating 0 and 4. 0 and 3. So whenever you have a definite integral, you do not need the plus c. So I end up getting here, I would get 3 to the 4th plus e to the 3rd minus 0 to the 4th plus e to the 0. And that's going to simplify to 3 to the 4th is 81. I would just leave e cubed as e cubed minus 0 plus 1, right? That's e to the 0 is 1. So I'd end up with 81 minus 1, so I would end up with 80 plus e to the 3rd power. That'd be my final answer. But you don't need the plus c. And the reason you don't need the plus c here is if you wrote the plus c. So we could have done it this way, like let's say our answer was x to the 4th plus e to the x plus, I'm going to make up a number for c. I'm going to pick 5. But then when I do the evaluation, I plug in 3, I get 3 to the 4th plus e to the 3 plus 5 minus, if I plug in 0, you get 0 to the 4th plus e to the 0 plus 5. But look, the constants, 5 and 5, they cancel out. Because it's a plus 5 here and it's a minus 5 there. So when it's definite like this, you don't need the constants because they always end up canceling out when we do the subtracting. So good question. Okay. So looking at the quiz 2 from Merckx, just to kind of address some of the questions. I know this question also is asked in the discussion, but I think it's worth looking at just because people asked about it. I'm going to start with question 3 from the quiz. Find the particular solution that satisfies the differential equation and initial condition f prime of x equal to x squared minus 2 over x squared, where x is greater than 0, which isn't super duper important, but just because you know. and f of 1 is equal to 1. Okay. So, right, there's like 3 different ways of saying you have to solve with a constant. You could literally say you have to solve with a constant, or you could say it's an initial value problem or an initial condition problem, or what did he call it here? He said to find the particular solution, right? So actually, let me address that phrasing in just one second. So I'm gonna find, right, I've got the derivative here, and I want to find f of x, the function that derivative came from. And so the way we solve something like this, right, we don't have an antiderivative quotient rule. We have to simplify that. So I'm going to rewrite f prime of x as, I like just dividing each thing by x squared. You can look at it like this. But some people don't like that. Some people prefer to think of it as, whoops. Come on, eraser. It might be time for a new eraser. This one's getting really gross and orange. You guys, can you see that? Not really. I can. Oh, look how orange it is. It's gross. Okay. Sorry. I was just noticing that. You could also write this as x squared minus 2 times x to the negative second. Either way you write it, you're going to get 1 minus. Now, you could leave it like this, but I would rather write it like this, because writing it as 2 times x to the negative 2 makes it easier to find the antiderivative of. Okay, so then anti-differentiating, the antiderivative of a constant is just that constant times x. So the antiderivative of 1 is just x. The antiderivative of negative 2 times x to the negative second is negative 2 times x to the, what's my new power going to be? It's going to go up here.
-1.
Yeah. Oh, yeah. Someone wrote it too. Sorry. And then we're going to divide by that new power. Plus c. So I've got f of x equal to x minus times the minus is plus 2 times x to the negative 1, or 2 over x. Either way. And so here's what I would say about this. This f of x equal to x plus 2 over x plus c, that is the general solution to this derivative equal to this function. And then we're going to find the particular solution by plugging in this value for x and this value for the function, which happen to be the same. So just make sure, right, whatever is in here, that's your x. And whatever's over here, that's what the whole equation is equal to. So I'm going to get f of 1, that's 1, equal to plugging in x equal to 1 plus 2 over 1 plus c, and then solving for c. So 1 equals 1 plus 2 plus c, subtract 3, negative 2 equals c. And then just like in the previous problem, well, the first problem, you have to actually write the answer is the function. So our solution is that the function f of x is x plus 2 over x minus 2, or plus negative 2. Right, so whenever you're asked to find the particular solution to an equation, to a derivative equation like this, or a differential equation is what that's actually called, the particular solution is the function where you have solved for the constant. Yeah, so those are good questions. Okay. Just a couple more quiz problems and then happy to take questions from the crowd. Also, just one more time, here is the attendance. Please go fill it out once and only once. Yeah, so let's look at, I'll look at question 1 from his quiz. Find an equation of the tangent line to the graph. So equation of the tangent line to the graph of y equal to the natural log of x to the 7/2 at the point 1, 0. So the way we find the equation of a tangent line in calculus is you're always just finding. So again, I should say really, we know the equation of a line. You can either write it as y equals mx plus b. That's not my favorite way to do it. I prefer to use the point slope form, which is y minus y1 equals times x minus x1. And we've already got, right, this is our x1, y1. So our equation is y minus 0 equals m times x minus 1. And our job, the only thing left to do, is to find the slope, which is m. Now, in calculus, the way we find the slope of a tangent line is by taking the derivative of the function and plugging in the point. Now, we can totally take the derivative of this function as is, but it makes sense to use rules of logarithms to simplify first. So you could either do it like this. Y equals the natural log of x to the 7/2, and then that power can come down, and we can say that y is equal to 7/2 times the natural log of x. So then if I take the derivative, my derivative here is 7/2 times the derivative of the natural log of x is 1 over x. So my derivative here is 7 over 2x. I will mention, if you did the derivative without using this simplification, right, if you just said the derivative of y prime, well, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, and the derivative of x to the 7/2 is 7/2 times x to the 7/2 minus 1, which is 5/2. You still actually get the same answer. It just looks way more complicated. This is still 7 over 2 times x to the 5/2 over x to the 7/2. But x to the 5/2 over x to the 7/2 is just x to the -1, or 1 over x, right? Because 5/2 minus 7/2 is -2/2 or -1. So this equals 7/2 times x to the -1, or 7 over 2x. Either way of doing it is fine, but I think it's way easier to simplify the logarithm first. In any event, we then plug in x equal to 1 to get that your slope, y prime, is 7 over 2 times 1, which is 7/2. And that's what's going to go in right there. So the answer to this question is y minus 0, or just y, equals 7/2 times x minus 1. And if they don't ask you to write it in the particular format, I would leave it like that. He didn't, but if you don't like leaving it like that, you can certainly distribute the 7/2 and get y equal to 7/2 x minus 7/2. Either way should be fine. But again, you might want to, well, I guess you can't really ask while you're taking the test, but he should specify if he wants you to write it a certain way. Yeah. Downside about the whiteboard, definitely getting the gross black dust all in my hands. I think this board is, not that I haven't cleaned it, but I need to clean it more frequently, I suppose. Okay. So still looking at this quiz 2 from Merckx. Sorry, where'd you go? Complete the table for the radioactive isotope round trip answers to 2 decimal places. Okay, this shouldn't be too terrible. They're probably, I would imagine they'll probably ask you some sort of radioactive decay or exponential growth question. So let's look at this one here. So the isotope, it doesn't really matter what it's called, has a half-life. So I guess I'll make the table, sure. Here's my table. I don't really care what the isotope is called, so let's just say the half-life is 1,599 years. You think they could have just rounded that 1,600? Would have made life easier for everybody. And the initial quantity, that is unknown. The amount after 1,000 years is 1.3 grams, and that value looks like it varied for different people because it's in red. And then the amount after 10,000 years. I really don't like the way this table is set up personally. That's also blank. So I would probably actually write it like this because it just feels like this is not so great. So here's what I've got. I've got time and I've got the amount. So I know that the initial value, actually I don't know. So time equals 0. I don't know how much I'm starting with. I know that after 1,000 years, I have 1.3 grams. And after 10,000 years, I have some unknown amounts as well. And I also know that after 1,599 years, I have half as much as I started with, which would be great if we knew how much we started with, but we don't. So, okay, fine. And this problem, I don't love the way this problem is set up, but it's fine. So I'm going to go with my usual model for exponential growth and decay. Y equals C e to the kt. And the way I'm going to deal with this is, well, I have to find C and K. And yeah, that's kind of lame, but okay. So I would probably find K first in this case, well, because C is supposed to be the amount you start with. So it's actually going to be a little bit harder to find. It's not terrible. We can find K though, just by saying, well, all right, I know that if I'm starting with, I'm just going to say 100 for a moment, but I'll show you 2 different ways to do it. So let's say we started with 100%. Okay, so C is 100%. We're going to change that. Then I've got Y equal to 100 e to the kt. And then I know that 1,599 years later, so when t equals 1,599, I'm going to have 50% of what I started with, or half of what I started with. That's why it's called the half-life. So I know that if I plug in t equal to 1,599, y should be 50%. So I'm going to have 50 equal to 100 e to the k times 1,599. Sorry, that's super small. I'll write that a little bit bigger. 50 equals 100 e to the k times 99. Solving for k, 50 divided by 100 is a half. You're always going to get a half over here if you're using the half-life amount. Equals e to the k times 1,599. Take the natural log of both sides. Natural log of 1/2 equals k times 1,599. And finally, k equals the natural log of 1/2 divided by 1,599. By the way, this is always true. If you know the half-life time period, 1,599 years, then the k value for that is always the natural log of 1/2 divided by the half-life. So not that you don't have to show this work, because he probably wants you to show this work, but you can always know in the back of your head, oh, if I know the half-life time, I know the k value automatically. It's just natural log of 1/2 divided by whatever that amount of time is. Okay, great. So now I can go back and say, my model is actually y equal to c e to the k, which is natural log of 1/2 over 1,599 times t. And then I can use this information to figure out what c actually is. So it's kind of like we're working backwards. Usually we find c first and then find k. Here we're finding k first and then finding c. So I'm going to plug in 1.3 for y and 1,000 for t. I'm going to get 1.3 equal to c e to the all this garbage times t, which is 1,000 years. And that should allow us to solve for c. So, sorry, I have to erase here. So solving for c, I'm just going to divide by all of this. So c is going to equal 1.3 divided by e to the all that. Sorry, it's a little bit gross. Natural log of 1/2. What's that for 99 times 1,000? And then you'd actually have to like, well, I think you can leave it like that. And if you want to round your answer, so then you have to use a calculator. And using a calculator, let's see. So if I was doing this via calculator, I would probably calculate this exponent first. So I would do, oh man, this dust just gets everywhere. It's gross. So I would calculate this by first finding, give it a little more light over here. First finding, let's see, the natural log of 1/2 divided by 1599, and then multiply that by 1,000, and then do e to the that. My wife is being super loud. Sorry. So e to the that, and you get 0.64, and then 1.3 divided by all that. And I'm getting 2.005. And since it says to round to the nearest 2 decimal places, that should be 2.01, just barely. Sorry. So c rounded is 2.01. So that's your answer to the first box. How much are we starting at times 0? And then to figure out how much I have that. So after that, the rest is pretty easy. That's going in right here. And then to find how much there is at time 10,000, we're just going to say y equals 2.01 times e to the natural log of 1/2 over 1,599 times 10,000. And you would plug in those values to a calculator and get some answer. I think I can leave that to you guys. All right. So one last question on this quiz that I will address. And actually, this is a good question to address in general because this is going to come up. And there's actually a nice way of doing a question like this. Well, I shouldn't say nice so much as maybe an easier way than actually using U substitution. So I made a couple of videos for you guys. I think I posted yesterday morning. One of those is called mini U substitutions, which I think is something that all of you, it's worth your time to kind of get a handle on because it's actually, I think it'll save you time in the long run. So some problems you have to actually do the U substitution, right? For example, so I'll circle back around to that last problem, the integral of 9 over 4x minus 7. We will definitely get to that in a minute, but I kind of want to take a longer path to get there because I think it's worth your time. Also, I need some water. So you should definitely watch the mini U substitution video, but I'm also going to give some examples of it right now. So let's say I wanted to find the antiderivative of, let's see, what's a good, let's do that. Of e to the 9x. Now, before we do that, what I want to actually ask is, what's the integral of e to the x? Well, we know this. The integral of e to the x is the best one ever. It's just itself. And so here's the thing. If I know the integral of e to the x is e to the x, I know the integral of 9 times x is going to be very similar in format. Right? The integral of e to the x, e to the x, the integral of e to the 9x is probably going to be e to the 9x with some modification. Now, here's my thought process in general. If I know that my derivative, right, if I differentiated e to the 9x, I would get e to the 9x times 9. I know that my antiderivative is going to make me divide by that constant. And there's a couple ways we can see it. One way to say, well, I'm pretty sure that my answer is going to be something like this. But here's the problem. The derivative of this isn't that. The derivative of e to the 9x is e to the 9x times 9. But I want this to have an antiderivative that's that, and that's not quite right yet. So what do? Well, I can divide both sides of this by 9, or multiply by 1/9. So I have 1/9 times the derivative of e to the 9x equals e to the 9x. But look, if I know the derivative, I'm going to bring this 1/9 inside, of 1/9 times e to the 9x is equal to 9x. Well, here's the thing. If you know the derivative of this is equal to this, then you know that the antiderivative of this is equal to that. So the antiderivative of e to the 9x is exactly 1/9 e to the 9x. Because the derivative would make you multiply by 9, so we have to divide by 9 to account for that. So what we end up seeing is that if you're integrating something where you have just a multiple of x, then you end up dividing by that multiple of x. But it only works for just like 5x or 7x or something times x. You can't do it for x to a power. Now, why do I call this a mini u substitution? Because you could do a u substitution here. You could exactly let u equal 9x. To wipe all my pens down. They all have like, sorry, I know it's not your guys' problem, but I'm going to complain about it. So let u equal 9x, and the derivative du dx is equal to 9. And I'm going to solve for dx. So I'm going to say du equals 9 dx. Dx equals 1/9. Hey, that's where the 1/9 is coming from, times du. So when I rewrite this integral, the dx becomes du times 1/9. And e to the 9x becomes e to the u. And then I usually write this constant multiple out in front of the integral. That's pretty standard. When you have some multiple of du here, that usually ends up going just outside in front. Because it's always going to be multiplied by the entire integrand, so it can always be pulled out in front of the integral. Okay, but then the antiderivative of e to the u is just e to the u. So I get 1/9 times e to the u plus c, which is 1/9 e to the 9x plus c. So here's what I'm going to say. I'm going to say it many times. If you're integrating something and you have a constant multiple of x, usually, sorry, let me back up. If you were to differentiate something and the chain will make you multiply by the constant multiple, the antiderivative is going to make you divide by the constant multiple. So a few more examples. And we'll work our way back to that logarithmic function, I promise. So the antiderivative of, I'm just going to do another example like that one, e to the 6x is e to the 6x divided by 6, or times 1/6 plus c. Because the derivative of 1/6 times e to the 6x plus c is exactly, well, the derivative of 1/6 times a function, the 1/6 multiple hangs out, and the derivative of e to the 6x, or the derivative of e to the stuff, is e to the stuff times the derivative of that stuff. But the derivative of 6x is exactly 6. And hopefully you can kind of see what's happening there. The reason I'm dividing by this 6 is because when I take the derivative, I end up multiplying by 6, and I need those 6's to cancel out. And then the derivative of this constant is just 0. So I get exactly e to the 6x. And that means I've done it right. If the derivative of this function is equal to e to the 6x, then the antiderivative of e to the 6x is equal to this function, 1/6 e to the 6x plus c. And this always works. If you're ever integrating something where instead of having x, you have a multiple of x, it's really just, you can use the pattern you know. So for example, if I was going to integrate sine of 4x, well, stop for a second, I know that the antiderivative of sine of x is negative cosine of x. So I know that the plus c, sorry, plus c. Sometimes we forget the plus c because we're being lazy. So if I know that the antiderivative of sine of x is negative cosine of x, I know that the antiderivative of sine of 4x is negative cosine of 4x divided by 4. Or you might prefer to write it as negative 1/4 cosine of 4x. Because when we differentiate cosine of 4x, we're going to get negative sine of 4x times 4, and that 4 will cancel out with the 4 down here, and we'll get an answer of sine of 4x as our derivative. Let me just show you the work. Right, the derivative of negative 1/4 times cosine of 4x plus c is, well, the negative 1/4 hangs out. The derivative of cosine of some stuff is negative sine of that stuff times the derivative of the stuff, which is just 4 plus 0. The 4 cancels the 1/4. The negatives cancel to give you positive sine of 4x. So hopefully this makes some sense. Whenever you integrate a function where you just have a multiple of x, you're going to end up dividing by the coefficient of x. Just like if you were differentiating that function, the chain will make you multiply by that coefficient of x. And it even works if you have a multiple of x plus a constant. For example, so I'm going to do these next ones showing less work. The antiderivative of e to the 3x plus 2 is e to the 3x plus 2 divided by 3. Or if you prefer, 1/3 the 3x plus 2. Because again, the derivative of this is exactly that, right? The derivative of e to the 3x plus 2 is e to the 3x plus 2 times 3, and that times 3 cancels out with the 1/3 there. Or the integral of cosine of 4x plus 7 is going to be exactly sine of 4x plus 7 divided by 4, or times 1/4. Let's see. Because the derivative of this will be cosine of your stuff times the derivative of that stuff, which is exactly 4, which will exactly cancel the 1/4. So those are mini U substitutions. You end up, and this is not official, that's what Grant calls them, that's what I call them. Typically, most teachers are okay with you doing those without actually showing the U substitution. So you shouldn't have to be like, oh, u equals 4x plus 7, du dx equals 4. He might want you to show that work, but the point is to get comfortable with these so you don't have to do all the work every time, because there's so much other stuff going on with integration that if you can do this just quickly, it'll save you some time. Now, let's go back to that question over there. In fact, yeah, where is this? So we know that the integral of 1 over x dx is the natural log of the absolute value of x plus c. And the same thing that's true for that's true for the previous things is true for this. If I was going to integrate, say, 1 over 3x, well, in this case, you could actually just factor out the 1/3. I'm not going to, but I'll show you how you could. The one way you write the answer is the natural log of the absolute value of 3x divided by 3. Or 1/3 natural log of the absolute value of 3x plus c. So this might seem kind of weird because, like, is that really the same? If I factor out the 1/3, I get 1/3 times the natural log of the absolute value of x plus c. Those don't actually look the same. What's going on here? Well, what's going on here is that these c's are actually different. And what's really happening here is that, where'd my green pen go? Is that natural log of 3x, you can break up. Right? You can write this as 1/3 times natural log of 3 plus the natural log of x with absolute values. And I didn't write the absolute values around 3 because I know the absolute value of 3 is 3. And then this is 1/3 times natural log of the absolute value of x plus 1/3 times natural log of 3 plus c. But this constant here, right, because natural log of 3 is just a constant, is what this constant here is. So they are the same, they just look different. But usually we got something more like this, like what's the integral of 1 over 5x minus 2? Well, here's the thing. I know that if I differentiate something with a 5x, I'm going to end up multiplying by 5. So when I anti-differentiate, I'm going to end up dividing by 5. And the antiderivative of 1 over something with just x to the first power, right, is really, really important. It's 1 over something with x to the first power. If it was a different power of x, you can't use the natural log rule straight away. So this is 1 over 5x minus 2. That's going to be the natural log of the absolute value of 5x minus 2. It's going to be almost that. What am I missing? Well, let's think about it this way. Yeah, exactly, Sophia. If I took the derivative of this, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. So the derivative of this, derivative would be 1 over 5x minus 2 times 5. But I don't want that times 5. So I need a 1/5 or divide the whole thing by 5, either way, to cancel out that 5 that you would get there. So just like the other mini u substitutions, you end up dividing by the coefficient of x. All right. Yeah. I'm going to do 2 more examples and we'll finally get to that problem there. So if we had 1 over, say, I don't know, 3 minus 8x, then the antiderivative of that would be the natural log of the absolute value of 3 minus 8x divided by negative 8, or times negative 1/8. Let's see. And again, you can check. You don't have to always check, but you can. Right? The derivative of negative 1/8 times the natural log of 3 minus 8x. I'm not going to find out right the plus c. Derivative of c is 0. That's going to be negative 1/8 times the derivative of the natural log of some stuff is 1 over the stuff times the derivative of that stuff, and the derivative of 3 minus 8x is just negative 8. Derivative of c is 0. And look, cancel, cancel. That's a 3. It looks like a 7 when I look at my board. So now to finally, right, there's a lot of build up to get to the question that was on the quiz, but to answer the question that's on the quiz, the integral of 9 over, what was it, 4x minus 7? Yeah. So this 9 on top, I think of as a multiple. I would write this as 9 times the integral of 1 over 4x minus 7. Right, because if you multiply this 9 through, it's 9 over 1, and the 9 multiplies 1, and the 1 multiplies 4x minus 7. So then, just using our rules, when you get 9 times, the integral of this is natural log of the absolute value of 4x minus 7. I left myself some room here though, because I know I'm going to have to divide by 4, or multiply by 1/4 with the 4. So I would write my final answer as probably 9/4 times the natural log of the absolute value of 4x minus 7 plus c. Okay, couple things. So there's the attendance form again, just in case someone didn't get it yet, although I feel like everyone's been here since I last gave it to you. I think those are all the things that I specifically wanted to cover. So do you guys have any particular questions? And it can be stuff from Merck's review sheet. It can be other things. But speak up or type something if you have a question. My volume is on. My volume is on. Just want to make sure. Some more U sub for sure. Gotcha. All right. Let's look at. Oh, I know there was actually. So yes, we'll do some more U sub, but there's one other thing I wanted to say real quick. So be careful with logarithms. So I just want to point out, you can't always use a logarithm if you've got 1 over some stuff, right? If you're integrating 1 over x cubed, it is not equal to the natural log of the absolute value of x cubed. Right? If we're integrating that, well, actually, if we differentiate this, right, the derivative of the natural log of the absolute value of x cubed is 1 over x cubed times 3x squared, which is just 3 over x, which is not the same as 1 over x cubed. So you can only use the logarithm rule, or you can only use logarithms really if you've got 1 over something with x, or if you do a u sub. Right? On the other hand, this integral, x squared over x cubed plus 1, this one we are going to be using a logarithm because, yeah, we'll look at that question too, Sophia. Here, I would let u equal, what would u equal here? What's a good choice for u?
Wouldn't it be x cubed plus 1?
So it could be that, or it could be the top. We should check both. So did you mean to say the bottom, Nicole, or are you correct? Either. So just, I just want to point out, if you let u equal the top, the derivative of the top is 2x, which we don't really have showing up. So in this case, the top is not an excellent choice. And I will say generally, the top is probably the last I said. Like sometimes the top is the right choice, but most of the time it isn't. But if we let u equal the bottom, which is x cubed plus 1, that's a good choice for both of the usual reasons. Reason 1, you can't see my thumb. Reason 1, it's the thing that's stuck somewhere else, right? Being in the denominator is considered being stuck. And thing 2, its derivative is also in the integral, or it's a multiple, right? We don't care about the constant multiples. So if I take the derivative of this, I get 3x squared. And as far as I'm concerned, I have a 3x squared. You can always adjust for a constant multiple. So as far as I'm concerned, oh yeah, we're good to go. I've got x squared, 3x squared, it's close enough. I just have to make it work. So I like to do it this way. I'm going to say du equals 3x squared dx, and then I'm going to divide by 3. So that 1/3 du equals x squared dx. Some other people like to do this thing where they do this, and then they multiply by 3 and divide by 3. But that's a way that people also do it. And then this 3x squared gets replaced by du. That's fine. That's not the way I like to do it. I like to just do x squared dx. That's going to equal 1/3 du. So I'm going to have, okay, 1/3 du over x cubed plus 1. That is my u. And then I would encourage you to get comfortable seeing it like this, that the integral of du over u is the natural log of the absolute value of u. But you can also rewrite it as 1/3 times the integral of 1 over u du, if that's easier to see. And then the integral of 1 over u is the natural log of the absolute value of u. So this is 1/3 times the natural log of the absolute value of u plus c. And then we have to plug in what u is equal to, which is x cubed plus 1. And we get this is equal to 1/3 the natural log of the absolute value of x cubed plus 1 plus c. And that's our answer. So you can definitely get a natural log something more complicated, but it can't just be 1 over x cubed plus 1. That would not have an integral of the natural log of x cubed plus 1. You'd have to have essentially the derivative of the bottom on the top. Okay. Yeah. All right. Let's look at. So Sophia asked a question in the chat. Let's see. Integral of, oh yeah. So I would like to imagine that he would not ask a question like this on a test. Not because it's impossible, just because it requires knowing the trick. And I know we talked about the trick, I think, last class, but if you don't remember the trick, it's kind of like, so here's the trick for a question like this. And I'll show you another one as well after this. If you have something like this, where you have a 1 plus e to the negative 2x or a something plus e to the 3x, you have to multiply the top and bottom by e to the opposite power. So I'm going to rewrite this as 2 over 1 plus e to the negative 2x times, let's use this green thing here, e to the 2x over e to the 2x dx. Always, so if it's e to a negative power, you're going to multiply by e to the positive power. If it's e to the positive, you're going to multiply by e to the negative. So then when we do this, we get the integral of 2e to the 2x over, so I'm going to have to distribute here and get e to the 2x times 1 plus, what is e to the negative 2x times e to the 2x? Exactly, it's e to the 0, which is 1. And now we can do the u substitution by letting u equal the denominator. So u is going to equal e to the 2x plus 1. And the derivative, du dx, the derivative of e to the stuff is e to the stuff times the derivative of the stuff, which is just times 2. So du is 2e to the 2x dx. And someone was extra nice. They made the top exactly equal to du. Right, that's my du. So this becomes the integral of du over u, or if you prefer, 1 over u du. And the integral of 1 over u du is the natural log of the absolute value of u plus c. And finally, we plug in what u is equal to, which is e to the 2x plus 1. So I get the natural log of the absolute value of e to the 2x plus 1 plus c. And then I'll just note, I would leave my answer like this, but you might see in solution manuals them dropping the absolute values. And again, the reason for that is because the insides e to the 2x plus 1 are always positive, so you don't have to have the absolute value. All right, so here's what I want you guys to do. I'm going to use the restroom because I have to pee, but why don't you guys try doing this one? The integral of 1 over 1 plus e to the 6x. So try that one. It's the same sort of process. You're going to multiply the top and bottom by e to the, well, I'm not going to tell you, but you can write it in the chat if you want. You guys should know what it is. I'll be right back. All right. Here's the attendance form again, just in case you need it. I think I heard someone just come in, which is fine. All right. So you would tackle this problem in exactly the same way we did the previous one. There's so much like orange dust on this card. I'm glad I put down like a little, you guys can't see it, but I put down like a little yoga mat rug underneath this whiteboard. And it's good because it's getting all this gross dust on it, and then I can go wash it. Okay, I know you guys don't care, but I care. So, I have here. So if we're doing this integral, we're going to multiply the top and bottom by e to the negative 6x. So we end up with the integral of e to the negative 6x over e to the negative 6x plus 1. And then the process is very much the same. We're going to let u equal the denominator here. Du is going to equal the derivative of this, which is e to the negative 6x times negative 6 dx. You can write du dx, but I I'm almost always bringing over the dx. So I'm going to have negative 1/6 du equal to e to the negative 6x dx. Those are the same. I'm going to replace that with negative 1/6 du. This is going to equal the integral of negative 1/6 times du over e to the negative 6x plus 1, which is just my u. So a lot of these problems turn out to be, what's the word I'm looking for? Sorry, brain work, logarithmic ones. So you get negative 1/6 natural log of the absolute value of u plus c, which is negative 1/6 natural log of the absolute value of e to the negative 6x plus 1 plus c. Okay. There's actually another kind of version of this problem, which I feel like he could ask you. Let me just make sure I'm thinking of it the right way. Yeah, I think I've got it. Yeah, okay. So here's a version of this problem, which might be too hard for this test, but might not be. So something like e to the x over e to the x plus e to the negative x. Yeah, that's a terrible problem, right? Yeah, this problem sucks. Then make sure it's not too terrible. Yeah. So this one looks awful. It's really not. I'm going to multiply it. So if you see something with e to the x's or e to the something times x, and you see positive and negative powers of this opposite to each other, and you're not sure what to do, usually multiplying everything by either the thing to the positive power or the thing to the negative power is usually a good method. And this could be good for e to the x. It would also work if it was e to the 4x, e to the 4x, e to the negative 4x. I'm going to multiply everything by e to the 4x, and look what happens. Assuming I set this up correctly, which I'm almost certain I did. So I end up getting the integral of e to the 4x and b to the 4x is e to the 8x. E to the 4x and b to the 4x is e to the 8x. And e to the 4x and b to the negative 4x is e to the 0, which is 1. And then once you've gotten here, we're back in the same situation we've been in the previous two problems. You're going to let u equal the bottom part. Your du is essentially going to be the top part, you know, up to a constant, being off by a constant. And then it should just be the natural log of whatever u is. So this one you would finish off by letting u equal e to the 8x plus 1. Your du is 1/8 e to the 8x dx. So 8 times du is e to the 8x dx. Let me just check one thing here real quick. I feel like I'm doing something stupid. I am doing something stupid. I'm making a small mistake, which is fine. My du is not e to the 8x divided by 8. It's e to the 8x times 8. Sorry about that. My du is e to the 8x times 8 dx, and then 1/8 du is e to the 8x dx. So I'm going to rewrite this as the integral of 1/8 du is replacing this whole part right here. Still have a u on the bottom, right? That's e to the x plus 1. So my answer is 1/8 natural log of the absolute value of u plus c, which is 1/8 the natural log of the absolute value of e to the 8x plus 1 plus c. Which seems maybe a little surprising, right? Because our original expression didn't have e to the 8x anywhere in it. So I'll say one more time, if you've got something with e's like this and there's no obvious choice for a u substitution, try multiplying everything by e to the either positive or negative power over the same thing, because that often is the trick for problems like this. I will also say, this one doesn't work without doing this, right? If you try letting u equal the bottom there, it's not going to help, because if u is e to the 4x plus e to the negative 4x, then your du is e to the 4x times 4 plus e to the negative 4x times negative 4. And I don't really have that anywhere useful. So it gets real tricky if you don't know to do this thing here. All right, we've got about 15 minutes left. What else do you guys want to see? Someone said more u substitutions. I can certainly do more u substitutions. There's a good one. Yeah. I mean, I'm happy to take questions, but I've also got examples I can do if you guys don't have them. So let's see, what have we got here? We've got the integral of dx over x times the natural log of x squared plus 3. Oh, I don't need another dx. I've already got a dx. And again, if you don't like this dx over, you are welcome to rewrite this as 1 over x times natural log of x squared plus 3 dx. Either way of writing, it's fine. So let me ask you guys, what seems like a plausible choice for you? If I had to guess, what would I guess? Well, here's the issue. I'm not really seeing anything whose derivative is also there. Right? I don't want to pick u equal to x. You never want to pick u equal to just x if you're doing u substitution. Because if you pick u equal to just x, you're just going to rewrite the same integral with the letter u instead of the letter x, and you won't have done anything. For integration by parts, which I know you guys started talking about, it's a different story. It's fine to let u equal x and dv be whatever, but we're not talking about integration by parts yet because it's not on your midterm tomorrow. But for this one, I wouldn't pick u equal to x. The only other thing I really have is natural log of x squared plus 3. So I'm going to go with u equal to the natural log of x squared plus 3. Not because it looks like its derivative is there, although it actually is, but because it's the thing that's stuck inside something, right? You've got this natural log of x squared plus 3 stuck inside this denominator here, inside these parentheses. So it seems like a plausible choice. Now, it might seem more plausible if I rewrote it as 2 times the natural log of x plus 3, where this power here is coming down in front. Because then my du dx is equal to 2 times the derivative of the natural log of x, which is 1 over x. And du equals 2 over x dx, and 1/2 du equals 1 over x dx. And look, I have a 1 over x dx. So before actually doing the substitution and changing everything to u's, I might rewrite my integral in the following way. I might rewrite it as the integral of 1 over this part, and I'm going to write that as 2 natural log of x plus 3 times the 1 over x times dx, because then it's easier for me to see, oh yeah, this part here, that's my 1/2 du. And this part here, that's my 1 over u. So then I can rewrite this integral as the integral of 1 over u. Wow, that's not a u. The integral of 1 over u times 1/2 du. I would really not write the 1/2 here. I would bring it out in front and write it as 1/2 the integral of 1 over u du. But then, just like every other time, right, you're going to do the integral of 1 over u a lot. It comes up often. The integral of 1 over u, so I should say I have 1/2 times the integral of 1 over u, which is the natural log of the absolute value of u, plus c. And then plug in u, which was the natural log of x squared plus 3. You get 1/2 times the natural log of the absolute value of the natural log of x squared plus 3. Plus c. Kind of gross, but that's what it is. Sorry. So that's how you do a problem like that. And again, I'll just point out, if you're not sure what your u should be, sometimes you have to guess. And sometimes you're going to guess wrong, which is fine. So in fact, let's see. I think I have another good problem here. Oh, sure, totally. No problem. Let's see what I want to ask about here. Okay, let's look at this problem, because I feel like this could be a problem. So we're going to do 2 different integrals side by side. We'll do this one first. The integral of, what have I got here? Sorry, where'd you go? Let's say x cubed over x to the 4th plus 1 squared, and then the reciprocal, x to the 4th plus 1 squared over x cubed. And although they look similar-ish, they're actually quite different. So for this one here, I can totally do a u sub. I can let u equal the stuff that's stuck inside the square and inside the denominator. And say, okay, u is x to the 4th plus 1. My du dx is 4x cubed dx, which I have, right? I have an x cubed times dx, and I can adjust for the 4 multiplying that. I can say 1/4 du equals, oops, sorry, there shouldn't be a dx here and a dx there. And you said you still automatically bringing the dx over. So it should be 1/4 du equals x cubed dx. And that's exactly equal to that. So it's going to get replaced with that. So I'm going to have the integral of 1/4 du over x to the 4th plus 1, which is u quantity squared. So then if I was to finish this off, I would rewrite it as, I'd bring the 1/4 out in front. And instead of saying du over u squared, which is not going to be a natural log interval, right? Because it's not over u to the first. I'm going to say u to the -2nd times du. And then I'm going to use the anti-power rule to finish this off. I'm going to get 1/4 times the antiderivative of u to the -2nd is u to the -2nd plus 1, so -1 divided by -1. And then I would simplify this as -1/4. Instead of times u to the -1st, I'd write times 1 over u. You don't have to do that, but I prefer to. And then I'd write -1/4 times 1 over, let's see, u was x to the 4th plus 1. Let's see. And that would be my answer there. -1/4 times 1 over x to the 4th plus 1. Or you could say -1 over 4 times parentheses x to the 4th plus 1. But I want to contrast that with this, because for this other problem here, we really can't use the u substitution. It doesn't make sense to let u equal x cubed, because the du would be 3x squared, and I definitely don't have a 3x squared. And I really want to make this point clear. It does not make sense to let u equal x to the 4th plus 1 here. Du dx would be 4x cubed, just 4x cubed. I keep wanting to write the dx over there. So this is the wrong path. We're going to erase it in just a minute. And then du divided by 4, or 1/4 du. Ugh, come on. That's equal to x cubed times dx. What I want to make absolutely essentially clear is I do not have x cubed times dx. I have 1 over x cubed times dx, and those are not the same thing. So we don't have this. So this is not a u substitution problem. There's no way a u sub works here. This problem is actually, so I'm going to erase all this. And this problem actually is just a simplification problem, really. So I can multiply out x to the 4th plus 1 squared. So this is equal to, let's see, x to the 4th plus 1 squared is x to the 4th plus 1 times x to the 4th plus 1, which is going to be, let's see, x to the 4th times x to the 4th is x to the 8th plus x to the 4th plus x to the 4th is 2x to the 4th plus 1 times 1 is 1. And then you just divide each thing by x cubed, so you get x to the 8th divided by x cubed is x to the 5th. 2x to the 4th divided by x cubed is 2x. And 1 divided by x cubed is x to the -3rd. And then we just use the anti-power rule. We get x to the 6th over 6 plus 2x squared over 2, or just x squared, plus x to the -2 over -2. Let's see. So sometimes things that look like they could be a u substitution actually aren't. All right, what else? Okay, I got one more. So going in a slightly different direction, just as a kind of reminder, there's probably going to be some derivatives on your test as well. I would bet good money that you'll probably see something like f of x equal to the natural log of, what have I got here? Sure. 2 to the x times x cubed plus 1 over cosine to the 4th x times the square root of x squared minus 3. And where they ask you to find f prime of x. And although you can certainly do this the hard way, you don't want to do it the hard way. What you want to do is you want to use your log rules to simplify this. So here's how this simplifies. So I'm not taking the derivative yet, so I'm just going to keep writing f of x until I actually take the derivative. So f of x is equal to the natural log of the top stuff. So 2 to the x times x cubed plus 1 minus the natural log of the bottom stuff. Cosine to the fourth x times, I'm going to write this as x squared minus 3 to the 1/2. And then natural log of a product, that's going to simplify as the natural log of 2 to the x plus the natural log of x cubed plus 1 minus, same deal here. It's going to be the natural log of cosine to the fourth x plus the natural log of x squared minus 3 to the 1/2. Now, I've actually made a tiny error here in that it's minus this whole natural log, so it's minus all of this. And what's going to end up happening is you're going to distribute this minus sign. So now I'm going to distribute that, and I'm also going to bring down the powers. So this x comes down, we've got x times natural log of 2. I can't bring this power down because there's not the power on the whole thing. So this just stays as the natural log of x cubed plus 1. This is the power, right? This is cosine of x to the fourth. So this is 4 times the natural log of cosine of x. And then this minus sign distributes, so I get minus 1/2 natural log of x squared minus 3. The way I remember what happens is all of the things on top have positive coefficients, and all the factors on the bottom have negative coefficients. All right, lastly, we differentiate. So the derivative of x times natural log of 2 is just 1 times natural log of 2, because natural log of 2 is a constant, right? You're not going to get 1 over 2. You're going to get just 1 times natural log of 2. The derivative of natural log of some stuff is 1 over the stuff times the derivative of stuff. Same deal here. Minus 4 times the derivative of natural log of some stuff is 1 over the stuff times the derivative of the stuff, which is negative x. And minus 1/2 times the derivative of natural log of some stuff is 1 over the stuff times the derivative of that stuff, which is 2x. And you could simplify this more by writing this as like 3x squared over x cubed plus 1, and this would be a plus 4 times sine over cosine is tangent. And this is you can actually cancel the 2 here and the 2 here and say it's minus x over x squared minus 3, but that's not the super important part. So I would be willing to bet you'll probably see a question like this on your test tomorrow for those of you in Marx's class. So that's all I've got today. Make sure you fill out the attendance form in case you didn't already. Just one time, please, just once. I will definitely try to get a practice test posted up soonish, and then I will post an announcement about it. I think we had a quiz due yesterday. If you didn't do the quiz, don't sweat it. If you've done it, great. If you still want to do it, you can. But again, focus on what's most important for yourself, which is probably studying for your test if you have a test tomorrow. I think that's it. If you guys have questions, you can always start a discussion, send me an email. And yeah, good luck on your test tomorrow. I hope it goes well.